Good afternoon. We should wait for someone else to join. And then we'll proceed, okay? Okay, maybe not. Maybe nobody else is going to show up. All right. Well, we'll just give him another minute or two. And then after that, we'll start. because I did say, I hope everybody got the message, because the weather is bad over here. And we don't want it to be too scary for anybody. All right, we got started now since nobody's showing up apparently. Okay, let's keep going. All right, so let me share my screen with you. And we can start on what we need to do. There we go. Fine. They show up. Okay. All right. We were looking at what were we looking at last time? Sorry, I forgot. Okay. Were we looking at Lewis structures? I think so, right? Yeah. Okay. That's what I thought. All right, so let's keep going on that. Now we're going to add a little more to it. So Lewis structures, we did, where is the assignment? Oh, there it is. The assignment's on here. We did the class practice, or did we? Okay. This is the one This is one of the things I need to find. I wanted to find a good video for you that tells you a different method than the one I teach. Okay, let me see what it'll do. Okay. It's got the normal Lewis structure. No, I don't want that one. I do the 5 easy steps too. Okay, let me see if that's on here. But this is only if you have a central atom, which is what I do anyway. Let's see.
At the end of this video, you'll be a pro at drawing the basic Lewis structures. There really are only 5 main steps that you need to know.
Now already
Let's get started.
said those.
Step 1. Find the total number of valence electrons for the molecule you're drawing the Lewis structure for. Let's try one. We'll use the periodic table to figure out how many valence electrons each element has. Hydrogen is in group 1 on the periodic table, so it has 1 valence electron. But the subscript tells us that we have 2 hydrogens. So we'll need to multiply that by 2. Oxygen is in group 6 or 16. It has 6 valence electrons. And when we add that up, 2 plus 6, we get a total of 8 valence electrons for H2O. Remember, valence electrons are the outer shell electrons. They're the ones that form chemical bonds and interact with the world around them. Let's try one more, cyanide. For cyanide, we could look on the periodic table again. Carbon has 4 valence electrons, and nitrogen has 5. The trick for this one is, though, it's a negative ion. This negative sign right here tells you that there's going to be 1 extra valence electron. So 4 plus 5 plus 1, 10 valence electrons for the cyanide ion. Step 2, put the least electronegative atom in the center. So how do you know it's the least electronegative atom? Just remember that fluorine is the most electronegative, followed by oxygen. So as you move away from fluorine and oxygen, atoms become less electronegative. That means those atoms will go at the center. Let's see how it works. When I draw the Lewis structure for something like NO2, I can see that nitrogen is further away from fluorine than oxygen. That means when I draw my Lewis structure, I'll put nitrogen at the center and oxygens on the outside. For something like PCl3, I can see that phosphorus is further away from the fluorine than the chlorine atom. So I'll put phosphorus at the center and the chlorines on the outside, like this. Some Lewis structures, like HCl, only have 2 atoms. In that case, you don't have to worry about it because there's no center. An important note, hydrogen always goes on the outside of Lewis structures. Always. Seriously. Let's look at HCl again. We know it has 8 valence electrons, and we'll put the first 2 in our structure between the H and Cl to form a chemical bond. That's important. By putting those 2 electrons there, we're showing that the hydrogen and the chlorine are chemically bonded now. Step 4, complete the octets on the outside atoms. Octet means 8. For HCl, we have a total of 8 valence electrons, 1 for the hydrogen, 7 for the chlorine. So we've used 2 already to form the chemical bond. For the chlorine, we'll put 4, 6, and then 8. We've used all the valence electrons, and we've completed the octet for chlorine. It has 8 valence electrons. For basic Lewis structures, the big exception is going to be hydrogen. It only needs 2 valence electrons for a full outer shell. So hydrogen has a full outer shell with 2 valence electrons. The chlorine, its octet is full with 8, and we've used only the 8 valence electrons that we have for the HCl molecule. We're done with this structure. There's one more rule that we need to look at. It doesn't apply to HCl, and actually it doesn't apply to a lot of molecules. But what happens when you've used all your valence electrons and you still haven't completed the octets for each atom in the molecule? That's step 5. So sometimes you run out of valence electrons and still haven't filled the octets. Hey, it happens, right? So in step 5, what we're going to do is if we run out of valence electrons, will move some of the valence electrons from the outside to the inside and share them and form double and triple bonds. Here's how it works. So for O2, oxygen, if I follow all the rules, I count the valence electrons, I have 12. And if I put a bond between the atoms and then fill the outer shell, I end up with a situation where I have an octet for this oxygen. It has 8, but this oxygen only has 6 valence electrons. It doesn't have an octet, and I don't have any more valence electrons. To solve the problem, I can take these valence electrons right here and move them to the center to share them and form a double bond between the two oxygen atoms. I'm still only using 12 valence electrons, but now this oxygen has 2, 4, 6, 8 valence electrons, and this oxygen has 2, 4, 6, 8 valence electrons. So by sharing those valence electrons, I can get the octet on each of the oxygens and still use the 12 valence electrons that I had for the O2 molecule. If I wanted, I could replace these right here with 2 lines to show the double bond, where each line represents a pair of electrons. For Lewis structures like N2, I would even use a triple bond to achieve octets. So how do you get good at drawing Lewis structures? Well, the first thing is know the steps. They're your guide. The second thing is practice. You need lots of practice to get good at this, for it to be second nature. Use the links in this video or go to my website and try more videos. First try it yourself and then watch the video. Pause when you're stuck, see what's going on there, and try to correct the problem. This is Dr. B, and thanks for watching.
Okay, so that's that one. Now, what I want to know is not this one. That's why I said that's the wrong one. I wanted the.
Welcome to Lewis Diagrams Made Easy with Ken's book. Today we're going to.
I want to start it. Hold on. Yeah, I need this.
At the end of this video, you'll be a pro at drawing the basic
but what I
structures.
need.
There really are only 5 main steps that you need to know. Let's get started. Step 1, find the total number of valence electrons for the molecule you're drawing the Lewis structure for. Let's try one. We'll use the periodic table to figure out how many valence electrons each element has. Hydrogen is in group 1 on the periodic table, so it has 1 valence electron. But the subscript tells us that we have 2 hydrogens. So we'll need to multiply that by 2. Oxygen is in group 6 or 16. It has 6 valence electrons. And when we add that up, 2 plus 6, we get a total of 8 valence electrons for H2O. Remember, valence electrons are the outer shell electrons. They're the ones that form chemical bonds and interact with the world
Let's see
around
if there's on there. Okay. I don't want one central atom. No, with no central atom. Like these guys. There we go. These are the ones I wanted to watch with you.
In this video, I'm going to give you a basic introduction into drawing
Let me go ahead and just.
So the first thing you need to be able to do is determine the
Sorry.
number of valence electrons.
I'm just trying to save these
Hydrogen
2
has
bonds
1 valence electron.
so I can put them up
So
for
when
you.
you draw the structure for hydrogen, it looks like this.
Okay.
Beryllium, which is in group 2, has 2 valence electrons. So this is the Lewis dot structure for beryllium. Carbon, which is found in group 4, has 4 valence electrons. And so when you draw a Lewis structure, you only show the valence electrons. Nitrogen has 5, oxygen has 6 valence electrons, and fluorine has 7. So first, you want to space out the electrons evenly before you pair them up. So oxygen, which has 6, you can draw like this if you want. And then fluorine has 7. So that's how you can draw simple Lewis structures of the elements.
Yeah, that's it.
Now, what about when these atoms combine and form molecules? What can we do? So let's say, for example, if we want to draw hydrogen gas. So each hydrogen atom contains a single valence electron. And hydrogen likes to form 1 single bond. So these 2 electrons will get together and form a single bond. So this is going to look like this. A single bond represents 2 electrons. So now let's look at another example. What about chlorine gas? Chlorine is a halogen, which contains 7 valence electrons. So if we draw the separated chlorine molecules or atoms, it's going to look like this. Now the halogens, like fluorine, chlorine, bromine, they like to form only one bond. And so these 2 electrons will be used to generate the single bond of the chlorine molecule. So this is how you draw the Lewis structure of Cl2. So as you can see, these 2 electrons were used to form the covalent bond within the chlorine molecule. Now it's very helpful to know the number of bonds certain elements like to form.
Mhm.
For instance, carbon has 4 valence electrons. And in order to get 8, it likes to form 4 bonds. It forms a bond to acquire a new electron. Nitrogen has 5 valence electrons. And in order to satisfy the octet rule, it needs 3 more electrons to get to 8. So nitrogen likes to form 3 bonds to acquire those 3 electrons. Oxygen has 6 valence electrons. It needs 2 more to get to 8. And fluorine has 7 valence electrons and only needs 1 more to get to 8. So fluorine likes to form a single bond. Oxygen likes to form double bonds. Now to the left of carbon, you have elements like boron. Boron doesn't follow this nice trend. In fact, boron doesn't want to gain 5 electrons in order to satisfy its octet requirements. Rather, it prefers to give away its 3 valence electrons. So boron likes to form 2 bonds. Beryllium prefers to give away its 2 valence electrons. So beryllium likes to form 2 bonds. So elements on the right side of the periodic table, like carbon and everything to the right of that, they like to acquire electrons. So therefore, you'll see that these numbers, they add up to 8. Elements to the left of carbon, like beryllium and boron, they like to give up their electrons. So the number of valence electrons tend to correspond to the number of bonds that they have, or that they like to form. So that's a general trend that you see as you continue to draw Lewis structures in the future. So let's draw the Lewis structure of oxygen gas. So each oxygen atom contains 6 valence electrons. I'm going to draw like this. By the way, when I draw an arrow, a full arrow represents the flow of 2 electrons. A half arrow represents the flow of 1 electron. Now we know that oxygen wants to form a double bond.
Mhm.
So each bond represents 2 electrons, so therefore we need 4 electrons. These 4 electrons will be used to create this double bond.
Mhm.
And so oxygen has 4 electrons left over that didn't participate in the reaction. And on the right side, we also have 4 electrons. So this is the Lewis structure of the oxygen molecule. Now, how can we draw the Lewis structure of methane using the same technique?
Okay.
Carbon has 4 valence electrons. And every hydrogen atom contains 1
See, that's how I do it.
valence electron. So when these elements get together to form methane, you can see that this is going to represent 1 single bond, this is another, and that's another single bond, and here's another. So methane looks like this. This is the Lewis structure for CH4. So let's consider our next example, ammonia. How can we draw the Lewis structure of ammonia? Now, nitrogen has 5 valence electrons, and hydrogen each contain 1 valence electron. So these two electrons will be used to form a single bond. That's another single bond, and that's going to be another single bond. So the Lewis structure for NH3 looks like this.
Mhm.
As you can see, nitrogen likes to form 3 bonds, as you mentioned before, and hydrogen likes to form 1. And in the last example, we see that carbon has the 4 bonds that it likes to form. So now let's try another example. Let's try the Lewis structure of water. Now, oxygen has 6 valence electrons, which I'm going to place like this. And each hydrogen atom only has 1. So these two will be used to form a single bond, and those 2 electrons will form a single bond. So you can draw the Lewis structure like this, but water does have a bent shape, so if you draw it with the appropriate geometry, technically it should look like this. So that's the Lewis structure for water. It has a bent shape. Now let's try another example. Let's try oxygen difluoride. How can we draw the Lewis structure for that? So oxygen has 6 valence electrons, and fluorine has 7. Now we know that fluorine likes to form a single bond, and oxygen likes to form 2 bonds. So this is going to be 1 bond, and there's the other. So the Lewis structure looks like this. So that's the Lewis structure of OF2, oxygen difluoride. But keep in mind, in reality, it has a bent shape, just like water.
Okay. He's going to go.
Now let's try a harder problem.
Yeah, that's the point I'm
Draw
looking
the
for.
Lewis structure for hydrazine and
N2H4.
2H. Now keep in mind, hydrogen likes to form 1 bond, and nitrogen likes to form 3 bonds. So because nitrogen likes to form more bonds than hydrogen, we're going to put it in the middle. So every nitrogen atom has 5 electrons, or valence electrons, and the hydrogen atoms only contain 1. So we need to form 3 bonds with each, or for each nitrogen atom. So we can say this is going to be 1 bond. This is going to be the 2nd bond.
That's a weird way.
Here, that's the 3rd bond. That's for the first nitrogen. These 2 can form a bond, and those 2 can form a bond. So right now we have a structure that looks like this. And as we can see that each nitrogen atom has 2 electrons left over, which we can draw as a lone pair. So that's the Lewis structure of hydrazine, N2H4. Now let's try acetylene, C2H2. So we have 2 carbon atoms and 2 hydrogen atoms. So every carbon atom has 4 valence electrons, and hydrogen only has 1. Now keep in mind, carbon likes to form 4 bonds, and hydrogen can only form 1 bond. So this is the only bond that hydrogen can form. So we can draw that as CH. And we could put a single bond between the 2 carbon atoms. We could also make another bond here. That's a double bond. Or we can make a triple bond. If we make a triple bond, each carbon atom will have 4 bonds. And so it turns out that this is the best Lewis structure for the acetylene molecule, C2H2.
Nope. Okay, so he did it the way that This is not how I do it. And that is exactly how I do it. I didn't want to look for that one. I cannot find one, but it shows you. Let me see this one.
In this video, I'll explain how to do these
They're all,
non-Lewis
yeah, they're all
structures.
central atom.
You know the Lewis structures, and then we have
No, we don't want those. Okay, anyway.
In this video,
So,
I'm
okay, so you saw how to do
going to draw
those.
simple Lewis structures.
Okay, let me go ahead and put my video on here. I'm just putting them in here because I want to keep them, you know, like I said, I like both of those that I had picked out. But anyway, so we did this worksheet last time in class. And I showed you how to do the puzzle, and there it is, the picture of all of them. Now, it is harder to do when you have something like this. So that's when I suggest that you do the 5-step method, right? Because the 5-step method, when you have a central atom, is the way to go. But when you don't have a central atom, you should do the puzzle. I call it the puzzle method. I don't know what anybody else calls it, but that's what I call it. Okay, so now that you know how to draw Lewis structures properly, we need to put a little more one more piece into the puzzle here. And that is coming up. Okay. So we're going to look at molecular geometry with this. And like I said, we're gonna know the different ones. Finally, okay. But we're gonna skip a few things. Okay. All right, so what does VSEEPR stand for? It stands for valence shell electron pair repulsion theory. What that means is that the electrons in an atom, electron pairs in an atom, will orient themselves in such a way that they will minimize the repulsion between them, right? Okay, so if you have these two atoms, and these are your bonds, they will be at 180 degrees because that's as far as away from each other as they can get. Okay, so you have two types of electron pairs in a Lewis structure. The bonding pairs, which we represent by a line. That's how I like to do them. But sometimes you can represent them by dots too, but they're dots in between two atoms. So that's how you know they're bonding. And then the lone pairs, which don't bond to anybody. Okay. For example, right here in this picture. Oh, sorry, no picture. But one thing to remember is that lone pairs, the ones that are not bonding, repel more strongly than bonding pairs, which means that the angle that we're going to be looking at is going to be less because they want to repel more away from it. So they're going to constrict the angle just a little bit. So they reduce the bond angle between the two atoms, okay? All right, so how do we determine the molecular shape? Number one thing is to know how to do that Lewis diagram or Lewis structure. And you do the same thing. And remember that once you are looking at the Lewis structure, each double or triple bond will represent just one area, not one pair, but one area of electron density, which is what we're going to call it rather than one pair, because it's really three pairs, but or two pairs. So we're just going to call it one area, of electron density. Here we go. All right, and that's how we determine the shape, is dependent on the number of valence electrons. There are lone pairs and the ones that are bonding in the central atom. This is only about the central atom. All right. So there are 8 common shapes, and here's the first one. The first one is 2 total areas of electron density, and both of them are bonding, so therefore none of them are lone pairs. Then that is known as a linear. An example of it is beryllium hydride, dihydride, well, hydride actually. There's another one. It's known as trigonal planar. And for this one, you need 3 bonds around the central atom, a total of 3 electron density areas. Like you see the white area right here is the electron density around the central atom. Don't look at the other part, just the central atom. There's 3 of them. And there are no lone pairs at all. You'll see what a lone pair looks like. It looks like a big goose egg on top. And that is a trigonal planar, like I said, and the angle between the bonds is 120 degrees. Then we have the next one, which is known as, see, there's the big goose egg that I was telling you about. Okay, this one is known as a bent shape, but it originates from a 3. So it is a bent shape from a trigonal planar. So in this case, you would have 3 total areas of electron density. That's the white areas, 2 of which are bonds, and 1 is a lone pair. Now, when we're looking at this, let me go back, and I'm going to give you a little bit of what I call a notation that is not on here, but it should be. So I'm going to just write it directly. I think I'm going to write it on the outside here, so that the first one that we're looking at, this one is an A for central atom, B for bonds, and 2 for how many, okay? So that's your linear, that's your AB2, okay? Now let's keep going. The next one's going to be AB3, right? So that one right there is an A, 1, 2, 1, 2, 1, 2, okay. A, B, 3, okay? The next one after that, that we were looking at, has 3 bonds, but 2 of them are bonds, and 1 of them is a lone pair. So in this case, we call it A for central atom, B for bonds, and E for electron pairs that are alone. Okay, so that's this one, okay? Next one after that is another choice, which is where we have, and this is an example, and of course the angle is less than 120 because we said that the lone pair will make this angle get smaller, remember, between the atoms. So in this case, between the bonds, I mean, the bond angle is going to be less than 120. All right, next one after that we have is, this is an example, and it is CH4, which you saw the guy draw, and this is known as a tetrahedron, and you notice there's 4 total, 0 are lone, and all of them are bonds. So again, to do this one, we're going to write it A, B, 4, okay? Because there's 4 bonds. All right, next one after that, I should have started higher because I'm going to run out of space. You have the 4, 3, 1. So in this case, you have 4 total. 1 is a lone pair and 3 are bonds. So for this one, the type, and I'm just going to write it up here, it's going to be AB 3, sorry, not 4. I almost did 4. I meant to do 3. 3E, right? Because we have one lone pair. And then the last one that we need to worry about, then we'll talk about the other ones, but we won't worry about them too much. These are known as an bent again. Oh, and by the way, I forgot to mention the bond angle for the tetrahedral is 105, 109.5, excuse me, and the one for the trigonal pyramid, which is the AB3E that we just covered, that's 107. And the last shape that we need to concern ourselves with, the other ones, like I said, I'll mention, but they're not necessarily part of this today. And that's for Chem 2, actually. So this one is going to be an AB2, right? Because you have 2 bonds and 2 electrons. So it's still a total of 4, as you can see. All right, so that's how these are. Okay, so this bond, the angle is going to be 104.5, like water. Okay, these are the other ones that we don't need to talk about, like I was saying, but these are the ones that I'm going to just write them here. This is an AB5. You have 5 total, right? There are variations of these too. This is known as a trigonal bipyramid, and the angles are 120 and 120 around the middle area, and 90 right here between the two areas, the 2 planes, because you have 2 planes crossing. All right, then the next one is 6. We're not going to talk about the ones that have lone pairs in these, just the regular. Like I said, I'm just mentioning them. And that was like example was PCl5. And the bond angles, once again, are going to be 120 and 90. We said that. Now these right here, there's 6 of them. So obviously the name of it is AB6, right? So sorry about that. I don't know what happened here. Let's go back. What on earth happened? It just went to the wrong thing. No, go away. Okay, here we go. So this is known as a octahedral. Octahedron. Sorry about that. I have to start all over again with this one. Okay, there we go. Okay, so the octahedron, that's AB6. And here's some examples of other types. Okay, so looking at this one, you can see that you have 1 lone pair and 3 bonds. So this fits this format, right? And that format is trigonal pyramid. I'm just going to call it trig pair because I can't write everything, but it's written down there, so I'll just show it to you. All right, so that one, PF3, is a trigonal pyramid, see? And it is 107, the degree angle. The next one we have is CO2, okay? You notice that this is one, remember, these are considered one area of electron density. So AB2, right? This one right here. That's a linear. CO2 is a linear. It's considered linear. Oh, hold on, let me erase this right here. And that's considered a linear because it is a straight line. The angle would be 180. See? And that's the end of our examples for here. All right, let me clear all of this. And remember, I told you guys we were going to do that other, let me see, go back to it. It's called VSEEPR Lab. Someday. Come on. Okay, so The VSEEPR lab is not your okay, there it is. Okay, so the VSEEPR lab is where we're going to go next. We are going to look at all of these Lewis structures. We looked at some of these, but we did not do the bottom part. And I told you guys that we would be doing these as a group, but you know, with nobody showing up, it's kind of hard to do it in a group. But as is, we're going to, let me download this. Now I can see it better. Okay, so there we go. All right, let me enable the editing on this one. So we can write directly on it. And I can't draw the Lewis structures for each one of these, but I can do all the other part. I can fill in the blanks on these. Okay, so the Lewis structure is already done here and it's done here. And if you look at it, there is an AB4, the electron groups are 4, the electron geometry is tetrahedral, number of bonded atoms is 4, molecular shape is tetrahedral. Still, resonance structures, there aren't any, and I am missing the bond angle. So I'm going to insert one more column in here, right here at the bottom here. I'm going to insert there. One more row below. Yep, there we go. And we're going to call it bond angle because it's not on here, but it needs to be. Okay, so this one, the bond angle is going to be, since it's tetrahedral, is 109.5. Okay. All right. Now let's look at the next one. All right. BF3, that's going to be, boron is an exception. So you're just going to have a boron molecule and you're going to have 3 fluorines around it like this. And if you do your math, which we're going to do because we don't want to be lazy and not do that, we're going to, oh, no, I'm just going to go ahead and type in right here. No, undo. Clear. No, not clear. Do the math. There we go. All right, so I'm just going to start typing in this one directly. All right, so you got 1 boron, right, times 3, because it's in group 3, plus you have 3 fluorines at 7 each. That gives you a total of 24, right? Since we use 6 of those, now we're going to say that it's over here. So we have, okay, so in this case would be 24, right? Minus, we have 3 bonds. Each bond is 2, right? So that would be 6. That's going to be equal to 18, right? All right. So now when we do the Lewis structure, we have 18 electrons to go, and I'm going to draw the electrons around the fluorines. And that's 6, that's 12, and that's 18. So boron, being one of the few exceptions that we have, do you remember it was groups 1, 2, and 3. There are exceptions, so they don't need but 6 for the groups, and the ones in group 3, 4 for the ones in group 2, and 2 for the ones in group 1. Okay, so the next thing to do is to write down here the type. Well, it's obviously a central atom bonded to 3 atoms, right? Okay, so it's an AB3, which tells me that we have 3 electron groups, right? All of the atoms are bonded. Therefore, this thing is a trigonal planar. Okay, and this same word comes over here because as long as, come on, stop doing that. Right, as long as you are having the same number of bonded atoms on both sides, right? They're both going to be trigonal planar, and I don't need a capital. I don't know why it has a capital. Okay, there we go. All right, the bond angle we said was 120. Just think of dividing a circle in 3, right? That would be 120. And the next part, we are not having any resonance because we have no double bonds. And the last part we will not do today. We will leave it alone. Now we're going to go to the next one. Okay, so I'm going to clear all of my scribblings, and that's where you should have put that in there and there. Okay, the next one is SO3. So we're going to do the math. 1 sulfur, right, times 6 plus, plus we have 3 oxygens times 6 also, for a total of 24, right? All right, so let's do what we know. Okay, so we know that we have an S, with 3 oxygens, right? That's your crude sketch. All right, that goes up here. And the next part is, okay, so since we have that, now we need bonding, right? Oops. All right, so we said we have, sorry, 24 minus. Okay, so once again, we have 3 bonds at 2 electrons apiece, right? Oops, 2, okay. That gives me a total of 18 again, right? Okay. Now, 18 electrons we are going to distribute among all of the S's. So that's 2, 4, and 6 there. We have 6 more here, that makes it 12. 6 more here, I know that's not a pretty O, but it'll work. That makes it 12 O, and that is 18. All right, we used all of our 18. The difference between this one and the one before is that sulfur is not an exception. And sulfur is going, wait a minute, you have cheated me out of 2 of my electrons. So what you do is you take these over here and you move them to the middle right here. So you now erase those after you move them. And there you go, that's your SO3. Now, this can have resonance, and the resonance would be 3 different ones. One of them would be an an SO3 with the one on top, right? And the other one could be one with the one on the other side, right? So like that. And yes, you need to put the dots and everything on there. And remember, you're doing this thing with the arrows, right? That they can all go around. All right, so clear all that. Now that we know, we looked at it and it was still 3 groups, right? There was no more than 3. So our next thing to do is to figure out what this is. Well, this might as well just copy it. Now I don't have to even write it because it is an AB3. Because even though you have more electrons around the central atom, they're the same areas. They're all an AB3. So this is, again, trigonal planar. We're going to copy that so we don't have to type it all. And yes, there were still 3. They're all bonds. So this is a trigonal planar again. Okay, so bond angle, everything's the same. But resonance, we had 3 resonance structures, right? Okay, and we can draw those if you want. Okay, so next is this one, CO2. Okay, let's do that one. Carbon, we have 1 carbon times 4, right? Plus we have 2 oxygens times 6. Oops. 2 oxygens times 6. Oops. I keep not holding on to that cap, the shift. Okay, so that's going to give us, I'm going to make them closer so that we have it all in one plane. Yeah, just like this one should have been all in one plane. Makes it easier to read. I think I'm going to do that with all of these. It makes it easier to read. This one didn't want to do it, didn't it? No, apparently because it's 32. No? Yeah, there we go. Okay. So this one is going to be a total of what? Let's see. 12 plus 4 is 16, right? All right. So we now need to make our crude sketch. Okay, so we got the carbon and 2 oxygens. And we always know that the carbon's the central because it's the one that there's only one of. Plus is less electronegative, like you saw in the video. All right. So we used 4 electrons because each bond is 4. So now we need to put that down and we say, okay, we have 16 electrons to begin with. Oops, no, not there. So you don't want me. There we go. We have 16 electrons to begin with, but we're subtracting 2 bonds, right, times 2, because that's 4 electrons a piece. And that's going to give me a total of 16 minus 4 is 12, right? All right, so we got 12 electrons. Now, we need to redistribute those electrons around the atoms that are not the central atom first. And we're getting a total of this many, right? That's 12. But carbon's going, wait a minute, you forgot me. I'm no exception. I need my electrons. So once again, what we're doing is we're taking these electrons, right? And we're moving them here. And that gives carbon only 6. So we need to do the same thing on the other side. So now carbon has its 8 and it's happy. So now the ones that we moved, we need to erase, right? Okay. And there's our Lewis structure. And as you can see, it's straight. There are no lone pairs and there's only 2 things. So the next thing to write on here is this general formula. That is an AB2. Okay, AB2, because there's 2 things bonded to the central atom. So number of electron groups is 2. That is known as a linear shape. We'll copy that again. And there are still only 2 in the central atom. There's only 2 bonds. And once again, that's linear. That angle is 180. And there are no resonance structures, even though there's a double bond, because that double bond, even if it shifted to this side, how would we know when they're both double bonds, right? So there's no way to know. Okay, so that's that one. On this one, we have one more to do, and then we'll be done with this part. Okay, the next one is ClO2. Okay, so math first. We have 1 chlorine in group 7 plus we have 2 oxygens in group 6. That's a total of 1 plus 7, 12 plus 7 is 19, right? But we also have a charge, so we need to add one more. And that gives us a total of 20. Okay, don't forget that the charge is included in here. All right, next thing to do is to do a crude sketch. Crude sketch tells me I need to draw a chlorine in the middle and oxygens to the side like that. Okay. Now, I know I just used a certain amount of these, right? So I need to subtract those. Don't forget, every step is very important. All right, so we have 20 electrons and we have 2 bonds at 2 electrons apiece. That gives me 16, right? Okay, so we have 16 electrons to go around. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then don't forget that since it is an ion, you need to mark, put it in brackets and label the charge, saying that this charge belongs to this molecule. Okay, so now we have a different kind of thing, don't we? All right, let's look at it closely and let's see what we can examine here. All right, so we have one, hold on, let me get the bonds in the one color. Let me make the bonds red. Okay, so we have, come on, red. It's not doing red. I said red. Oh my Lord, there we go. All right, so we have the bonds in red. So we got 1, 2 bonds in red, right? And then we have something else around the central atom. Let's make them green. All right, and we have 1, 2 around the central atom. So we have 2 different types of things around the central atom. Therefore, that tells me that this here is a, let me see, write this down. Okay, first of all, let's get rid of that. Okay, so this, as you can see, is an A because it's a central atom bonded to 2 atoms, and it has 2 electron pairs. So that is an AB2E2, which makes it a bent. Okay, but we still have 4 electron groups, which means that this would have been a tetrahedral molecular electron group geometry, but only tetrahedral. Okay, sorry, tetrahedral. So only 2 of those are bonds. Therefore, this is a bent molecule. The angle here is going to be 104.5. And there it is. And there are no resonance structures. Now, we will do more next time. And this is it. All right, we're done.